Here, let's give some examples analyzing the vessel's node. So, what shall be the causes or deviations that are expected to happen? Let's say here that the deviation shall be no flow, for example. The cause shall be whether there is some manual valve that was closed by mistake, or that the control loop failed. Maybe the instrument air itself was cut from the valve, and since the valve fail action is fail close, this shall cause overpressure in the upstream system. So, what shall be the consequences in case of no flow? When we analyze the consequences, we don't consider safeguards. We are temporarily considering that there are no safeguards, then afterwards we shall analyze the safeguards. So let's see what shall be the consequences here. The main one shall be the overpressure as we said, but what shall happen in case of overpressure? Well, the consequences shall be catastrophic. The upstream piping rating is 900 and the downstream rating is only 150. This is because the design pressure of the upstream system is 120 bar gauge, which is the well shut-in pressure, while the design pressure of the downstream system is only maybe 10 bar gauge, for example. So if some blockage occurred here, the downstream system with 150 pound flange rating is prone to failure. In addition, there is another consequence which shall be the loss of production. So when the inlet flow stops, the downstream system may work for some time depending on the level of the vessel. Then afterwards, there shall be no more production, which means a loss of profit because there is no product to be transferred to the downstream system and hence there is a shutdown. Yes, there is another separator train to where some flow may be directed, but still we cannot predict how much flow shall be directed as each separator has its flow controller. And the flow controller has its set point, and even if some flow was directed, this doesn't mean that all the flow will be the total flow to our separator here. So some overpressure can happen at the end. So what are the safeguards the design is considering here? Here we are having a HEPS system as a safeguard. The HEPS system stands for High Integrity Pressure Protection System. As we can see here, there are 3 pressure transmitters acting with a 2 out of 3 voting. So if one pressure transmitter is giving a false reading, still the shutdown action shall be considered if the other 2 are functioning. So the pressure transmitters send their readings to the shutdown system. If at least 2 of the 3 transmitters read a very high pressure reading, the shutdown system shall send a signal to close the shutdown valves. HEPS system usually has 2 shutdown valves to ensure redundancy. Valves shall be closed once they receive the signal from the system of the very high pressure. So this is a strong safeguard with high integrity. There is also another safeguard which is related to the operating procedures. Operators should be well trained, and in order to open or close some valves, this should be under specific procedures. But still, human error is probable. We also have pressure alarms that may warn the operator. However, we should also take into consideration that the pressure rise is expected to be too fast that the operator won't have time to respond. In addition, we don't guarantee that the operator shall respond quickly to the alarm, especially if the plant has many nuisance alarms that are not really needed. This shall reduce the sense of criticality to the alarm when the operator hears the alarm. So are these safeguards enough? This shall depend on the discussions within the meeting between the operation team, the design team, and the HAZOF coordinator. People may have different opinions, and sometimes even the opinions are biased if this means back-charging cost on the contractor, which is the owner of the design, or making the operation more difficult, which may be resisted by the operation team. Here we can have some solutions. The first solution, which can actually remove the risk, is to consider the whole system here to the last isolation valve as fully rated, which means that all this system shall consider the 900 rating. So here, all the piping after the HEPS system, along with the manual valves and control valves, can withstand the 120 bar gauge of the well. In this case, there is nothing to be afraid of. This is usually the common practice we follow in most systems. However, if we are talking about a well in an area that is different from that of the separator, or if it is feeding multiple separator trains, this shall mean that we need to replace a huge amount of piping with another piping of much higher rating, which would be very costly. That's why in most oil wells, this is how it shall work. Another solution can be considered, which is to add a pressure safety valve. This valve shall be set at the maximum pressure the piping can withstand. But here there is another issue, which is the destination of the relief liquid. It cannot be sent to the flare, of course. Maybe if there are no valves in this area and all the valves are close to the separator, we can direct the relief liquid to the separator. However, this is a scenario that needs an extensive study as it may lead to unexpected consequences. Here we choose to protect the system through HEPS, which can replace the PSV in such cases where PSV is not applicable or needs a specific system. These are the most effective solutions that can increase the system's integrity. But as we can see, these can be costly solutions and may lead to other scenarios. However, there are much simpler solutions that shall reduce the frequency of the overpressure causes. So we have seen the most effective solutions that can increase the system integrity. But as we see, these can be costly solutions and may lead to other scenarios. However, there are much simpler solutions that shall reduce the frequency of the overpressure causes. So in our case, I myself see that even if placing HEPS here is a strong safeguard, we can have some solutions to reduce the frequency of overpressure or to even negate it. Reducing the frequency will reduce the criticality of the loop and the probability of its failure on demand. This is something that is studied more in depth during the cell assessment, which usually follows the HAZOP. So let's have a look at the P&ID design. Also, if we are afraid that an operator closes a valve by mistake, we can consider all the manual valves here to be locked in the open position. Here we are ensuring that these valves won't be closed unless an operator with a high authority gave permission to close them, which shall give much higher level of security and reduce the probability of overpressure due to a valve being closed by mistake. We can also change the valve fail action to fail in the open position. In this case, we have guaranteed that if the instrument air was cut, overpressure won't happen here. Still, it can happen if the valve was mechanically stuck in closed position or if the control loop gave a wrong signal for some reason. So here we must take care that changing the valve fail action shall cause more flow to the vessel, which can cause liquid accumulation. Checking more flow shall come in the next deviation that shall be studied separately. But it's important here to highlight that the level accumulation will take much more time than overpressure in the system. So the operator here will have time to take some action. So here I shall add the last two suggestions as recommendations to update the P&ID and consider the valve fail action to be fail open. And the manual valves here shall be locked in the open position.